Hello. Thank you all for participating in this online course. First, I would like to thank the CIMPA and ICTP for their kind support and for providing me this opportunity. I would also like to express my thanks to Professor Polish Fordenbach for a kind hospitality during my stay at the TU Darmstadt University. I learned a lot from him, and we had great discussions. So, as the title suggests, functionals have a very important role in my presentation. So, I will start with functionals and simple concepts, and then move into the advanced and new research topics. Let E be a vector space over the real numbers R, and let G be a subspace of the vector space E, and assume that we have a linear mapping from G to R. Now we look for an extension like F from all of E to R with the properties that at least a certain property of G remains valid for this F. So F certainly over G is this one, and we have linearity everywhere. And the property that we need to transfer on F. The answer of this is the so-called Banach analytic theorem that says with these assumptions, a certain property here is a mapping, is a function from E to R. So let P be a function from E to R with these properties. Yeah, lambda x is lambda P of x for all positive lambda and x in P. And P of x plus y be less than P of x plus P of y. This is a sublinearity sort of. And assume that G from a subspace of E R be a linear map with this property that P of x less than P of x for all x in G. The point is that by this theorem, it follows that there exists an extension F from all of E into R such that you know that it is extension, and so F restricted to G would be G. But the interesting point is that we have this property F of x is less than or equal to P of x, but for all x in P. The proof is elementary. Indeed, the idea is using Zorn's lemma. I remind Zorn's lemma very quickly. It says that if we have a, for example, an partially ordered, indeed, partially ordered set with this property for all Q subset of P that is totally ordered, then there exists a maximal element. This is maximal in P. The maximal means that if the order here like this, and if X is greater than F, then X equals to F. And we don't have any element greater than F. So we start to prove this theorem. As mentioned, the idea is to construct a P. So we define some P like this, all edge from the domain to R. This is a subspace of P with these properties. First, G be a subspace of D of H, and obviously it's a subspace of P. And we have this property for H. H of X less than P of X for all X in the domain of H. So here I mentioned that these elements are linear. The set P is non-empty. We know that because at least we have the element G. So it is non-empty. We want to define an order here, and the order is defined like this. We say that for H1 and H2 in P, H1 less than H2, define only if we have these conditions. Yeah, H1 is a subset of H2 and H2 restricted to the domain of H1 be H1. It's easy to check that. It's an partial order set. Or partial order, yes. So it is a partially ordered set, and it is non-empty. Let's view the totally ordered subset of P. We want to find. I forgot to mention that Zorn's lemma says that if any totally ordered subset of P has a bound with this order, then there exists a maximal element. So here we need to show that Q has a upper bound by this order. Like this. We may write Q like this. And to define a bound or an upper bound for Q, we define first H from E of H to R like this. P of H be the union of all of the domains of the elements in Q, and H of X be I of X if H be an element in P of H. Is it due to this property? It is well defined, and so H is an upper bound for Q. So by Zorn's lemma, there exists a maximal F, maximal elements F in P, and this is the answer. This F is the extension that we are looking for. How? We just need to show that F of X, this F, the domain of F is all of the vector space, because the other properties we see here hold. We have this inequality for elements, and F is an element of P. We just need to have this one, the domain, be the E, the vector space. So, how to show this equation whole? To do this, we may assume that they are not the same, and we have, by contradiction, that there exists some x0 in E minus P of F. And we define a set by this one, P of H, be the domain of F plus R x0. You know that the procedure is that we want to find some H greater than F in the way that they are not equal, and so this contradicts to the maximality of F. So the domain is like this, and we define H over this element plus, for example, T x0 be exactly F of X plus T alpha. You may be wondering which alpha here is. We determine alpha in a way that H be an element of P. And for this, we need to have this inequality, F of X plus P alpha be less than P of X plus P x0. We need to have this one. And by the first property of P, we know that the first property of P is T of X be T of T multiplied by T P of X for positive T, strictly positive T. And by dividing both sides on the constants, we may write having this is equivalent to have this one, f of x minus alpha less than p of x first class, and also f of x minus alpha, because we have a vector space and we have this property. So it is easy to dividing the sides and obtaining this one. If we prove this one, this statement, then it follows that H is an element of P because these two are equivalent. So for proving this one, we look for F is linear. So we may write this, and by the sublinearity of F, because we have an element F in P, we have this one, and by the properties of P, we have also this one. So we can write, before using this one directly, I clean up this, and here I have an x0 here. So I can write like this, less than by the triangle inequality, and that sublinearity plus x0 plus y minus x0. And by rearranging these inequalities, we have f of x minus f of y minus p of y minus x0 less than p of x plus 0 minus f of x. We note that this one implies that p of x plus x0 minus f of x greater than alpha, and this one implies that f of x minus x minus x0 less than alpha. So we have this one here and this one, but x here is arbitrary in the domain of f can be chosen, and we have this inequality. Here we have this for all x and y in the domain of f. So by taking lim-sup on the left side and limit on the right, we obtain an f such that f of y minus y minus x0 less than alpha, and this one on the right. So this is equivalent to this property. So we have found an H from the domain of H to R with this property. H is greater than F, and F is not the same to H, because the domain of H contains domain of F, and they are not equal because X0 is in the domain and it's not here. So this is an elementary but very important theorem. I will continue to present some applications of his theorem. The first one is about the dual of a space. From now on, E will be a norm space. And E star for a norm space, E star will be defined all the linear mappings from E to R. They are linear and continuous. This is the notation, and we may define a norm for F, either the supremum of f of x, the absolute value of f of x, for x in the unit ball. And it is an elementary, that's elementary notion to prove that this is a norm and other properties. As you know, I want to apply Banach analytic form to obtain this corollary. Let G be a subspace of E, and G be a linear mapping from G to R, which is continuous. And from this, you know that the norm of G is finite. At this, there exists some f in x star that the norm of f is the norm of G. Here, I mentioned that it is the sup of G of x for x in G. But here, it is defined like this, the sup of the absolute value of f of x. We may also remove the absolute value. They are the same because the vector spaces are in this presentation on R, and here for x and E. It is interesting because the sup here, besides that f is an extension, this property, the norm of G, I mean, remains valid for f. So how we can use the analytic form of Banach to this corollary? It's easy, because we defined P of x or P from E to R, X to, I need to have this one for all of P. And I have G here. First, I need to define G, and also I need to define some P that is sublinear and have the property that is greater than G of X. And G from G to R I need to have this one less than P of X. So P of X can be defined like this, less than the norm of G, the norm of X. So we define here in this way. For all X, we may define like this because G is a certain constant. So for F by Banach, theorem, there exists an extension from all of E to R such that F of X less than P of X. This is the norm of G, norm of X. And by taking supremum on the sides, on the unit ball, we deduce that the norm of F less than norm of the norm of G, and the converse one is obvious because F is an extension of G, and this one is obvious. So we arrive at the result. Another corollary is interesting, and it is very useful for people who are working on the geometric properties of Banach spaces. For any x0 in E, there exists F0 and E star with this property. The norm of x0 equals to the norm of x0 equals to the norm of f0, and f0 of x is the norm of x0 to the power of 2. Here, this is a notation that we may use instead of f0 of x. The proof is elementary. Since we have a x0, we define E like this, and also we define P from G to R like this. T x0 and I need to have this one T, the norm of x0. You see that G is linear, and we may have an extension for G with the same norm. So by the previous corollary, we may here it is easy to write that the norm of G is linear and the norm of G is exactly the norm of x0. By the previous corollary, there exists x0, which is an extension of G from all of E with this property that the norm of f0 is the norm of E, and it is an extension that's f of x0 is x0 equals the norm of x0. I need to make a change here because I need to have a 2 here. So I need to change here in advance be the t, the norm of x0 to the 2. And this equality is easy because I change this one. I need to check this y. The norm of G is the norm of x0 here because the norm is defined on the unit ball. And here, this is the soup of G of x for x in G. And the element of G here are the form of E x0. So it would be the soup of G of Px0 such that the T multiplied by x0 less than 1. And so this is like to write x0 here the norm of x0 to the -1, and so we have this one. At least we can write the soup of G over this one, x0 over the normal x0 over x0, and this is exactly the normal. I said that it is important to study the geometric properties of Banach spaces. Usually, a duality mapping using this result can be defined like this one. J of x is all the elements in E star with this property. The norm of x is the norm of f, and f of x is the norm of x to the 2. So from this corollary, we deduce that J of x otherwise is non-empty. But the question is that is this G single valued? Because we have it multiplied, multiple valued from mapping from E to E star. The answer is that for Hilbert spaces, and, for example, LP spaces for P between 1 and infinity, we know that this mapping is at least single valued. But what about the other spaces? We will call this property smoothness. We show that if G is single value, then the norm of the space is differentiable, they get two differentiable, and they are equivalent. But the question is that the finite dimensional Banach spaces or finite dimensional norm spaces, is G for that spaces single valued? There is an example here that is interesting because if we consider E, the three-dimensional space with this norm. First, we consider norm 1 on the elements x1, x2, x3. My norm 1 is the absolute value of x1, x2, and x3. And by this norm, I write this norm infinity, and this is the maximum of xi, I between 1 and 2 here. You know that both of them are norm spaces, and you know that for finite dimensional spaces, the norm is complete and they are Banach spaces and other thing. But the question is that is G. First, let that E has this norm, L1. And it is an elementary exercise to show that a dual of this space is exactly E with norm infinity. And we may define E from E star by first one. So the norm is L1, and for the dual, we have the L infinity norm. J here is not single value. So we deduce that this norm space is not smooth. And the norm of E is not get to differentiable. By this is the example. We may consider, for example, x b 1 over 2 and 0, and if 1 be an element of the dual, here dual is the R3 with the same R3 with this norm L infinity, and this one be 1, 1, and 1, and F2 is defined 1, 1, and 0. You know that they are not equal, and we know that the normal F1 and F2 are the same, and the norm of X is the sum of 1 over 2, 1 over 2 is 1, and we have F1 of X equals F2 of X equals 1. It's easy to show because by the property that we have here, so J is not single valued because both of them belongs to J of X. So we have problem to the spaces even in finite dimensional space for the duality mapping. I show you the ball for both of them, or the sphere here. The first one, the sum of x1, x2, so it is in R2 I show. This is the ball that we have for the first one and for the second one, the maximum. For two-dimensional is like this, and you see that we have some points that seems not to have a smoothness property, or the derivative of the norm cannot be defined here by the definition that we will see soon. And there is a result by James that says that if J is single valued, then the space is reflexive. This is interesting. And how about reflexive spaces? A reflexive space will be defined very soon. Is a space that E with the E star are equal by this injection. N of X is defined on the elements of E star by this F of X. If this N is onto, then the space is said reflexive. And for reflexive spaces, it is easy to check something interesting for these properties. And something else about the corollaries that I cleaned up. We defined F by this way, F of X. And on the other side, we define X like this one. We find some J, I write it like this, J of X as an element in Jx on the X. And by this, we deduce that the norm of X is exactly the suit of F of X for the elements in the unit ball. And by the corollary and indeed by Banach theorem, we deduce that this supremum is attained. And there exists someone that achieved here, and we may write by maximum. And if here is E star. And the question is that, how about the first one? And As mentioned, we may find the solution in reflexive spaces. So the Banach theorem in geometric forms are more interesting, I think. The first one, so to state this geometric forms first, we need to define hyperplanes or affine hyperplane. If you consider R2, the lines that through the region are indeed hyperplanes, but the lines that doesn't through the region are called affine hyperplane, as you know. But in norm space, hyperplane is defined like this. All the x and e that f of x equals alpha here. It is important that we assume that f here should not be 0. This is an scalar in R. And here we assume that f doesn't vanish 0. So you know that here there is no assumption on the continuity of f. But there is a result that says if f is continuous, we have that h. There is a notation that we use for this one. This is close, and they are equivalent. This is an elementary result, and I skip the proof. And how about the application of this definition? Let A and B be subsets of E. We say that an hyperplane H separates, or affine hyperplane H separates A and B if we have this statement. There exists alpha such that so we say that H separates A and B if there exists alpha such that we have, for example, f of x for all x in A less than alpha, and f of y for all y in B be on the other side. Geometrically, we can say that the separation says that A lies in one of the half spaces and B completely, entirely lies on the other side. And strictly A and B are strictly separated if and only if there exists alpha and epsilon and also H with this property. F of x less than alpha minus epsilon for all x in A and alpha plus epsilon less than f of y for all y in B. We are in the position to state the first geometric form of Banach space. Banach theorem. First geometric form. Let's A and B be two convex subsets of E. So they are both convex, and assume that their intersection is empty, and assume also that one of them is open. For example, A is open. Then there exists F or H that separates both of them. A and B. The proof applies Banach analytic theorem. And we need to prove some lemmas first. This lemma is interesting because introduces the gauge function or Minkowski function. Let C be a subset of E, which is open and convex with this property. And assume that 0 is an element in C. Define P of x. Here is familiar because we had someone like this. P of x here, we define the infimum of positive alphas with this property. Alpha inverse x, P in C. Why it is defined? Because we have here C and 0 is an element in C, and we define this for all x in. If we consider x here, we want to make it to approach this 0. And how we can do that? It's easy, because if we consider here x over n, and by tending n to infinity, we see that xn goes to 0 here. And so between these denominators, we consider the indeed the minimum or the infimum one if we couldn't find minimum. And so we consider all the alpha because we have this one. In denominator, we have alpha, and by tending alpha to infinity, we see that this one goes to 0 and belongs to C, but it is not economical, and it is better to define this gauge function, and P has some properties that I mentioned here. Then the lemma says that P satisfies these properties. First one is that P of x less than the norm of x, and this is, you see that it is positive, and indeed we need to find some n with this property, and also we have this property, another property that C exactly is the set of x in B such that P of x is strictly less than 1. And it is very interesting and a nice representation for C. Also, P has the properties of the analytic form upon Banach here for positive lambda and the sublinearity. We should prove 4 properties for this gauge function. The first one is easy because we may consider a circle or a neighborhood here, or a ball with radius r, and there exists a positive r with the property that P of 0 and r is a subset of C because C is open. So we have this one, and then for any x in E, we know that x over this term belongs to this set. This is easy because the norm of this is exactly R, and we have this inclusion. So it's easy. So from this, we have x less than, by the definition of P, P is the infimum of alpha with this property. And here has the role of alpha. So P of x here is less than norm of x over R. So we may take here M 1 over R. The second one is also easy. If we consider x in C, this property, we want to show that we have this property. C is open. Since C is open, we deduce that there exists epsilon greater than 0 with this property x plus epsilon x belongs in C. It has a roll-off radius here. And then we have 1 plus epsilon x in C. And by the definition of gauge function, we deduce here that p of x less than 1 over 1 plus epsilon. And this one obviously is less than 1. And then we have the result here, that C is a subset of this set. C is a subset. And for the converse, let x have this property that p of x be less than 1. So we may consider some alpha and 0, 1 with this property. X over alpha belongs in C. Because p of x is less than 1, and it is easy to find this one by the property that it has, the gauge function. And then for x, we may write this convex combination x over alpha. And since C has a 0 point, we may write alpha multiplied by this fraction and 1 minus alpha 0, which is a combination that this one is in C and 0 is in C. So we have an element in C. And the properties that these two properties that we had before, we use this to is easy. For the first one, we may write pt of x by the definition is the impedance of positive alpha, which we have this one, and this is by rearranging. I'm trying to obtain the result. I write this one and the t here, maybe write on the denominator like alpha over t, and we may write t, the continuum of alpha over t with this property, and this is exactly t of x. And I skipped the proof for this one. It is easy and elementary, and we need another lemma to prove the first geometric form of Banach space, this lemma. Let C be a subset of C with these properties: non-empty, I write like this, open, and convex. With this property, let also x is not an element of C. Then we may separate both of them. For example, if we have C like this and this is x0, we can find an hyperplane that separates both of them. The proof, if we prove this one, indeed we have proved the main theorem by a combination of these lemmas. We don't have the assumption that C contains 0, but by translation, we may always assume that 0 is an element of C because we are working with linear mappings and everything is linear here. And we have made this assumption. And we may here, by this assumption, define the gauge function. And by gauge function, we consider first G as Rx0 and define G from the subspace G to R like this, defined by Tx0, B T, which is linear, and this T, G of Tx0 has the property that less than G of T0. This is indeed the usual element of G. This inequality is easy. We may take two cases. If T is less than or equal to 0, everything is obvious because in this case, we have T0 and by linearity, T, which is negative elements always less than P of X0 because this one is positive.
Right, that's slightly bigger. They've asked online. It's okay. It's readable, but maybe just a little bit bigger.
Oh, yes.
Yeah, and you can check the questions over there.
Yes. Thank you. Yes. More bigger. It is big enough, I think. And for positive T, it's 0, which is T, and less than T, because this one is greater than 1. Why? Because P here is a gauge function and greater than 1 because X0 is not in C. C is a set of X such that P of X less than 1. And X0 is not an element here. So it is greater than 1. And so we have this inequality for this case. So we have proved this one. It follows from Banach theorem, analytic form, that there exists a functional f, which is an extension from E to R, extends f, extend G, and it has the property that f of x less than p of x. For the particular case that x is x0. For this one, because it's an extension over x0, is exactly 1. And f has this property, f of x always less than p of x. And we prove that by that lemma, the previous one, less than m the norm of x. So f is continuous here. And from the other inequality that proved in the first lemma, we know that for all x in C, f of x, we know that we have this one, and for x in C, the gauge function is less than 1, and 1 equals f of x0 as mentioned here. And this is the proof of the lemma. We separated C from x0 here. The proof of the theorem, Banach theorem. First, geometric form. We may consider C in that theorem because for that theorem we wanted to separate A and B. We consider C as the A minus B, which is the algebraic form A minus B by A in A and B and B. And T is convex because the form of A minus B is convex here. The first set is convex, the second is convex, and so this one is convex. And it is open because it is y minus A minus y, this union for y in B, and A is open, A minus the single point y is open, and the union of open sets is open. And we know that the intersection of A and B is empty set. So we know that 0 is not an element in C, and we may apply the previous lemma to find some f from x star by the previous lemma with this property f of. We may write for the element in C, for example, x minus y less than 0, and we have separated 0 from C by this one. And we may write this f less than f of x less than f of y, and by taking lim sup on the left and limit on the right, we obtain an alpha between this A and B. The infimum here is the left side, for example, x and A, and y and B. And the first geometric form of Banach theorem is proved. And how about the second geometric form? Upon Banach theorem. It says that if we have A and B, one of them is closed and convex, and one of them, the other one is compact and convex, and both of them non-empty. Then we may separate them strictly in the sense that with a distance they can be separated. And we define the definition of strictly separation. Proof. Set again A minus B like before, and C is here again convex because A and B are convex. And here we have a new property for C that is closed. Why it is closed? Because it is a minus of a closed and a compact set. And if we have, for example, A minus B converging to, for example, C, and without loss of generality, we may assume the second one, for example, B is compact, and we may write this one converges to B, and then we may write, in this case, converges to C minus B plus B minus B. And we see that the first one is in B and the second one in B, and so it is closed. And we know that 0 is not an element of C. And by this, there exists a positive R such that P of 0 and R, the ball with the radius R intersection C is non-empty. Because 0 is not in C and C is closed. We may write this. And by the first theorem, there exists a hyperplane that separates this one from C. So there exists definitely E star, which is not 0 and separates 0 and C, and in the way that f of x minus y less than f of rz for all z in B of 0, 1. And for all x and y in A and B. And then it follows that f of x minus f of y less than this one by minus. We may use, because here z is in this ball, and we may write r f of z, and by taking lim in here, we have this one, and now let epsilon be 1/2 r norm of f which is a positive number because f is not zero, and this implies that f of x plus epsilon less than f of y minus epsilon. And by taking lim superior and lim inferior, we obtain alpha, and similar to the previous theorem, we obtain an alpha and separates. This shows that the separation is completed. So there is a remark here that for the finite dimensional spaces, we know that there exists always a functional that separates them, and but we don't have, for the general case, the strict separation. But we have another result here that is interesting. Let F be a subspace of E, or this is a linear space, and assume that it is not dense in E. We may obtain an F and E star that's not zero, but restricted to F, it is zero. So in the case that F is not dense in E, we always have such F. If we use the converse of this one, the negation, I mean, for the cases that we want to show that a subspace is dense in a space, we just need to show that if a functional is zero over the subspace, then it would be zero on the entire space. We may prove this by Banach geometric form theorems. And it let x0 be an element in E, and assume that x0 is not in the closure of F. And we define A this closure of F, and we will zero set. This F is indeed a subspace of E. So it is convex, and B is singleton and convex, and it's compact. This one is closed, and we may strictly separate F bar from zero, and so there exists F by Banach geometric form with this property. And since here X is taken in F bar, and F bar is a linear space, so we may tend some scalars to infinity and show that we have by linearity, we did use that, of X is zero for all X in F, and this is the result that we wanted to show. The next section is weak topology. cycling the board up first. Suppose that X is a set and Yi be a family. Of topological spaces. And assume that we are given a collection of mappings like Yi from X to Yi. The question is that can we construct a topology on X in a way that all the mappings phi be continuous? The answer is yes, because we may consider the discrete topology. But the discrete topology is not so cheap. Indeed, it is the most expensive one. We just need to have these mappings be continuous or equivalently phi I inverse omega I be open in the topology that we are going to construct. For the open sets in Yi. In topology, for creating such a topology, the best way is first to construct the bases of neighborhoods for the points, and we need just to consider phi I omega I for the finite intersections where omega I is an open set in Yi. We see that this set defines a base for neighborhoods of indeed elements, and then we may use the arbitrary unions of this intersection. This is the topology that is the best one and has the fewest open sets that still makes the functions phi I continuous. This topology is called the weak topology with respect to the functions phi I. And we use it in the way that, a simple way. Indeed, in the case that the mappings, let me be the norm space that we had before. And so this is the X for us. And define phi I like this, phi X star from E to R. And here the topological space Yi, all of them be R. And the topology that we construct, which is weak topology, is the finite intersection and then arbitrary union of these finite intersections. And we may define this base like this one. Or before I state this one, I want to mention some properties of this general form. In the case that we have, I explain it here, if Z be another topological space, and if we have a function from Z to X and from here to Y, because it is a useful lemma, and this is so phi I, assume this is phi I, psi, and this one is continuous, psi is continuous if and only if phi I, or psi I is continuous. And it's easy to show that because we just need to use some elementary properties of set theories like this one, the intersection arbitrary, the union arbitrary intersection finite, and psi inverse, phi I inverse. Omega I is exactly phi I psi inverse omega I here, and the union and intersection are here. And so if this one is open, and if we have this composition continuous, then we obtain this one, and the converse is also easy to show. For this case, which we call the weak topology, the topology on E such that all these mappings are continuous is denoted by this, and it is called the weak topology on E. And it has some easy properties. The first one is that E and E star power source. We consider 2 points, x1 and x2. We want to have 2 neighborhoods, weak neighborhoods indeed, that have no intersection. For this, we define A, x1, B, x2, and as you know by the geometric form of Banach theorem, we may separate these 2 sets and obtain F in E star with this property that F of x1, they are indeed strictly separated because they are these single points are compact, and we may define O1, the first one be phi F inverse minus infinity, and O2 phi F inverse alpha and infinity. You see that the intersection of O1 and O2 is empty. So it is Hausdorff. And the basis of neighborhoods for x0 is defined for x0 like this. X such that fi x minus x0 less than epsilon, the absolute value. For example, I from A1 to K. And here, epsilon K and Fi varying arbitrary, and this neighborhood can be constructed, and why it is indeed open in weak topology, because it can be written like this: phi inverse Fi AI minus epsilon AI plus epsilon. So, as you remember, this one is weak open, and the intersection, finite intersection of open sets is open. I write here some easy properties of the convergence of weak topology in weak topology. Xn goes to X in weak topology if and only if this is the notation that we use for the weak topology, or we may write here. This property is mentioned in the definition of weak topology, and Xn goes to X strongly by the norm topology implies that the convergence in the weak topology, they are easy because, as you know, the weak topology has fewer open sets, and this is easy. And also, we have this implication, then the normal is bounded, and we have this inequality. It follows, the boundedness follows from the known theorem that we may mention it here as uniform boundedness principle. And because if we have this one, then f of xn for all fn x star is bounded. So xn is bounded in the norm topology. And the inequality here is easy because f of xn less than the norm of f, the norm of xn, and by taking lim-inf, we obtain this one goes to f of x, and we, for this one, we may write lim-inf of xn times the norm of f, and by taking supremum in the left side, we obtain supremum on x, because we have in the for f is 2. For f, we know that this one is the norm of x, and we have, for f less than 1, we have this term. And some other properties of weak topology, like this one. If Fn strongly goes to F and Xn tends to X weakly, we may deduce that Fn of Xn converges to f of X, and it is easy to show because by this inequality listen, we may write Fn minus F Xn plus F and X minus Xn, and this one goes to 0 because this one strongly converges and this one is bounded by an easy inequality, and the second one is by definition. And the question here is that why we are weakening the topology here. Because in weak topology, we have more compact sets, and for this reason, we even want to weaken more this topology to weak star topology. But first, I mentioned some other results. I don't know. Yes, we have time. This proposition is existing for finite dimensional space. If is finite dimensional, then the weak topology with the weak topology is the same that if has the norm topology. The proof we know that the norm topology has more open sets, and we just need to prove that norm open set is weak open. And so let X0 be an element in E, and we consider a neighborhood like U of X0 in the strong topology. We have to find some Vx0, the neighborhood for the weak topology, with the property that we a subset of U. And to do this,
we have a seminar here in
10
minutes.
So completely. It will be finished in 2 minutes.
Okay.
Let R be a positive number with this property. It is possible because U is a strong neighborhood of x0. We want to find a weak neighborhood for x0 in this wall. If we do this, so we have proof that u x0 is indeed weak open. For doing this, we consider a base like this for E, and then we may consider this space with norm 1, and we consider this decomposition of X, xi, ei, for every element, and we define I from E to R. For all X, the decomposition of X goes to the constant xi, this coefficient, and we define. By using this functional, they are indeed continuous and linear, so they are in U star, and we may define. We like this. Fi x minus x0 less than r over k for I from
sorry, we
finish.
have like a research group for the journal class.
Oh yes. 20 seconds.
All right.
X minus x0 then can be written like Fi by this decomposition, and using this one, since x in V, we have less than the constant k, r over k, which is r, and so x given V of 0i. Thank you. That's all, and it's finished for today. Thank you for your patience.